Good evening and welcome to your final chem video for the first semester. Woohoo! You made it! Today we will be using math to determine the formulas of compounds. So let's get out your calculator, your pink sheet, and let's finish up Chapter 7. So our new thing we're going to look at is percent composition. So we're going to take a formula and find out what percent of that formula each element contains. So in definition, it is the percent by mass of each element in a compound. The formula you're going to use is taking the molar mass of the element and dividing it by the molar mass of the compound. And then, of course, because it's a percent, we're going to multiply it by 100. So we're going to find the percent composition of Cu2S. So how do we begin? First thing we're going to do is find the molar mass of the compound. So Cu has a mass of 64. We know there are 2 of them, so we're going to multiply it by 2, and we get 128 grams. We're going to add that to S, which is 32, and we are going to get an answer of 160 grams per mole for the compound. Once we have the compound's mass, we find the percent of each element. So we're going to take the total mass that element contributed to the formula and divide that by the total formula mass. So for Cu, I am going to take 128, not the 64, because I have 2 of them. So I want to take the total that it gives to the formula. So I'm going to take 128, divide that by 160, and multiply it by 100. And that comes out to 80%. Well, that should mean sulfur is 20%, because we can only have up to 100%. So let's double check ourselves. Sulfur would be 32 over 160 times 100, and indeed it does come out to 20%. Let's find the percent composition of BaNO3 Mass of Ba, 137, plus N, which is 14, times 2, which is 28, plus our oxygen, which is 16 times 6, because again we distributed that 2, which is 96. Add them all together, and we got 261 grams per mole. So now to find the percent composition, we're going to take each element individually. So for Ba, I would take 137 over 261, multiply it by 100. So I get about 52.4%. Then I'm going to break up NO3. Because I want to find the percent composition, I'm going to break it down. So we're going to take N individually as 28 over 261 times 100, and we get about 10.7%. And finally, for oxygen, we would get 96 over 261, multiply it by 100, and we get about 36.8%. Now, if I wanted to know the percent nitrate, I could do that too. Just combine the 2 masses of N and O and take that over the total also. So sometimes we see weird formulas like these. These are called hydrates. And we often want to know what is the percent of water in this hydrate. As we do this, we're going to do it the same way, but we're going to focus on one part only of the formula. Now we have this dot here. that just tells me that for every zinc sulfate, I have 7 waters. What I'm going to do is just add the 7 waters to this formula. I'm not going to multiply it. A lot of you will make that mistake and try to multiply because the dot often seems like multiplication. But this is just a way to show a formula is a hydrate. So let's begin by just getting the mass of the formula. Zn is 65. Adding it to sulfur, which is 32. Adding it to oxygen, which is our 16 times 4, which is 64. And then we're going to add it to our waters. Since I want to know the percent of water, I am not going to break this down into hydrogen and oxygen. I'm going to leave it together. So I know I am going to need the mass of that. So I need 7 times my waters. So hydrogen is 1 times 2, or 2. Oxygen is 16. So 2 plus 16 is 18. Now I'm going to take that 7 times 18 and get 126. So to find my formula, I add all of these together and I have a total mass of 287. So again, wanting to find the percent of water, well, this is water. So I am going to take 126 over the total 287, multiply it by 100, and I get 43.9% water. So we used part of the compound instead of all of the elements individually, and questions may ask you for that. But again, do the same thing. You totally need the mass of everything and then break it down for what they're looking for. What if we're given the percent? So we're going to work a little bit differently when we do this. So we know magnesium hydroxide is 54.87% oxygen by mass. So it's saying in the whole formula, I have 54.87% oxygen. I want to know how many grams of oxygen then would be in 175 grams of the compound. So I know my compound has a mass of 175 grams. I know 54.87% of 175 is oxygen. So how do I do this? I'm going to do straightforward math. I'm going to find a percent of a whole. So when we look at this, we change this into 0.5487, and then of means to multiply. So what I've done is I've taken the percent, so I take 0.5487, multiply it by 175, so I know I have 96 grams of oxygen. When we use math to determine chemical formulas, what we're going to find most often is the empirical formula. The empirical formula is the symbols of the elements in a compound. Where the subscripts show is that the empirical formula is not necessarily the true formula of the compound, but it does give us a ratio of the elements to each other. How do we use math to calculate empirical formulas? Often we are given the percent composition of the element, or of the compound I should say, and what percent of each element is in that compound. So what we're going to do is we're going to convert that percent composition to mass. Basically, it's real easy. All we're going to do is change the percent sign to grams. So we're going to assume that there is 100 grams. So all we're going to do is change the percent sign. Then we need to convert mass to moles. So this is where that other math comes in. So when you're converting from mass to moles, remember you need to divide by the molar mass. And where do you find the molar mass? On your periodic table. Then you're going to divide all the moles that you get. So you've changed all your masses into moles of all of the elements in the compound. And you're going to look at all of those numbers. And you're going to divide them all by whichever number is the lowest number of moles. When you do this, we're going to then get a whole number. And this is going to be the ratio. However, because we are dividing, we may not always get nice round whole numbers. We're going to get some that end in decimals. If any number ends in 0.5, we are going to multiply all of our numbers by 2. So let's practice. It's easier to show it than to just talk about it. So we want to find the empirical formula of a compound that contains 63.52% iron and 36.48% sulfur. First thing you want to do is change your percents into grams. And remember, we don't know how much is there, so we assume it's 100, so all we have to do is change our percent signs to grams. So for iron, I'm going to change it to 63.52 grams. For sulfur, I'm going to change it to 36.48 grams. Second step was to change grams into moles. To change grams into moles, we divide by the molar mass. So I'm going to divide both of these by the molar mass. So we go to our periodic table and we look up the molar mass of iron, and that is 56. And sulfur is 32. And then we plug it in our calculator. So iron comes out to be 1.134, and sulfur comes out to be about 1.14. Now, how many decimal places you should report? I would probably do about 2 as an average. If you start rounding this number, your numbers at the end are going to be off, and thus your formula is going to be off. So I would do 2 at the least. If you want to do a couple more, that's fine, but I would definitely stick to at least 2 decimal places for this number. So this is now in moles. Once I'm in moles, what I want to do is look at which number is smaller, and then I'm going to divide by that number. Well, 1.13 is smaller, so let's make sure that I'm just going to take off the 4 and make sure it's the same as the one below it. Just makes math a little bit easier. So 1.13 divided by 1.13, and we get 1 and basically 1. This then is my ratio. And from the ratio, then we can get the formula. So it's saying I have 1 Fe and I have 1 S. So let's do it again. So we want to find the empirical formula of the compound found to have 26.56% K, 35.41% Cr, and the remainder is oxygen. So we know that for K, we have 26.56 grams. Remember, all we're doing is changing the percent sign to grams. For Cr, we have 35.41 grams. We can't forget that we have oxygen in this also. However, it doesn't give me a percent, but it does tell me that the remainder is oxygen. So if we have percents, all of our percents have to add up to 100. So we know if we take 100 minus 26.56 minus 35.41, whatever is left over is our percent oxygen. And our percent oxygen comes out to be 38.03%, which means 38.03 grams. So now we go through and we divide each by their molar mass. So molar mass of K is 39. Molar mass of Cr, or chromium, is 52. And molar mass of oxygen is 16. This time, since oxygen is part of the compound, we don't need to use the 32 as if it was a Hofbrinkel, because it's going to be part of a total compound. Then we just need to do our math on each of these. So for potassium, we get 0.68 moles. For chromium, we also get 0.68 moles. And for oxygen, we get 2.38 moles. So now we're going to go through and we're going to find out which one is the smallest. So 0.68 is the smallest of all my moles. So I divide by the smallest. And I do it for all of them. So for potassium we have 1, for chromium we have 1, and here we have 3.5. Now remember, I said if something ends in 0.5, we have to multiply everything by 2. So once we get to that ratio stage, so here are my ratios. Once I hit the ratios, not earlier, we don't care about what these end because we're going to divide them again anyway. But once we get to our ratio, we know we can't have half of an element. So what we're going to do is we're going to take each of these and multiply it by 2. Even though just my oxygen ended in 0.2, since this is a ratio, we have to now, whatever we do to one, we have to do to all of them. So if I'm going to multiply this one by 2, they all must be multiplied by 2. So when I multiply these then all by 2, I'm going to get my new ratio of 2, 2, and 7. So this is the ratio I'm going to use to then build my compound. So my compound is going to be K2 Cr2O7, which if you go to name it is potassium dichromate. Let's do one more. Analysis of a 20-gram sample of a compound containing only calcium and bromine indicates that 4 grams of calcium are present. We want to know the empirical formula of the compound. So I know I have Ca, which I have 4 grams of, and I have bromine. Again, they don't give me any information on bromine, but they did tell me I have 20-gram sample. So 20 minus 4 equals 16. So the remaining sample must be the bromine. So I have grams. Divide through by your molar mass. So Ca is 40, Br is 80. So Ca's ratio comes out to 0.1 moles. Br comes out to 0.2 moles. Now I still divide through by the lowest number of moles, so divide by 0.1, and I'm going to get 1 and 2. So here's the ratio I'm going to use to build CaBr2. So again, just another way of using math to get the formula. Now remember, your empirical formulas were not necessarily the true formula. So how do we get the true molecular formula, which is our actual formula? Well, to do that, we need to know the empirical formula. So to find our molecular formula, we're going to take the mass of the molecular formula, which they usually have to give you. Otherwise, I don't know how you're going to really figure this out. So they should give you the molecular formula mass. Then you're going to divide by your empirical formula mass. This is the one that you're going to calculate. So you're going to have found the empirical formula, and then we're going to look them up and add them up, and we're going to calculate this. Divide the two, and that gives you a number x. And then you multiply all of your subscripts in your empirical formula by this number x, and that is going to give you the correct formula. Again, we know the empirical formula is a ratio of those elements to each other. So if we multiply 1 by x, we have to multiply them all by x to keep that ratio. And then of course, you're not going to reduce back down, because otherwise all you're going to do is reducing back down to the empirical formula. So, for example, we've gone through the math and we have the empirical formula of a compound is P2O5. Through experimentation, we find that the molar mass of that compound is 283.89 grams per mole. And we want to know what is the molecular formula. So we're going to take the molecular formula mass, which is 283.89, and we're going to divide it by the empirical formula mass, which we have to calculate. So we know the empirical formula is P2O5. So we just need to look it up. So P is 31, and since we have two of them, we multiply by 2. We add it to our oxygen, which is 16, and we have 5 of them, so we multiply that by 5, and then we add the 2 together. And we get 142, so that's going to go up here, 142 grams per mole. And you'll see those will cancel, which is good because we don't want a unit that we're multiplying some subscripts by. So then, once again, just plug it in your calculator, and you'll see we get about 1.9999, so that is close enough to 2. Again, you want a whole number. If this ends in 0.5, once again, multiply it by 2, because you can't get decimal answers as subscripts, because you have to have whole elements that are combining. So what we're going to do is we're going to take this 2 and we're going to multiply it by P2O5. So basically distributing the 2 through to my subscripts. So then my new formula from this becomes P4O10. So this is the empirical formula. This is the true molecular formula. So let's try one more. We're going to determine the molecular formula of a compound with an empirical formula of CH and a formula mass determined to be 78.011 AMU. Remember, AMU is just atomic mass units, basically the same thing as our molar mass. So we're going to take our empirical formula and we need to find out its mass. So C is 12 plus H, which is 1. So that's going to give us 13. Now we can take our molecular formula mass, divide it by our empirical formula mass, and we're going to get a number. And I get 6. Again, multiply that by your empirical formula, which is going to give us C6, H6. So what if we are not given the empirical formula? So we have a sample of a compound with a mass of 34 AMU is found to consist of 0.44 grams of H and 6.92 grams of O. And we want to know its molecular formula. Well, you can see we can't just add the 2 and get 34. And since we don't have an empirical formula, guess what you got to do? You got to find one. So we're going to start it the same way. We're going to take hydrogen, and we know that we have 0.44 grams, and oxygen, which has 6.92 grams. Divide it by its molar mass, and we get 0.44 moles of hydrogen and 0.43 moles of oxygen. Then we divide by the lowest number of moles, so 0.43. And we get our ratio. So this is going to give us our empirical formula. So I have H and O. Now I need that mass. So I know I have 1 plus 16, which gives me 17. So that is my empirical formula mass. Now I have to take my molecular formula mass, and I need to divide. If ever you forget which one needs to go on top and which one needs to go on bottom, know you can never have a decimal. So your larger number always has to go on top. So I have to take 34 divided by 17, and I get 2. Multiplying that by my empirical formula, and my final molecular formula is going to be H2O2. So it's just taking the two ideas and combining them together. So now you have several different ways of finding a formula. You can take it from a name and work it out that way, or you can take it from math and calculate it. I hope you have enjoyed first semester, and for those of you leaving us, good luck, and for those of you staying, I hope we can continue to have more fun.